All right, morning everybody. Today we were scheduled to have an inverted lecture, but we're a little bit behind on where I wanted to be in chapter 15. So we're going to continue on, and we're going to move the inverted lecture to Friday. So I think that'll just work out better overall. So today we're going to talk about substituted benzene. We're going to talk about if you have a substituent on benzene, does it activate or deactivate the ring towards electrophilic aromatic substitution? Not all benzenes are equally reactive, depending on what their substituents are. And we're going to talk about what happens when you have a substituent on a benzene ring. Where does the next substituent go? And it depends on what that first substituent is. And so we're going to talk about ortho, para, meta directors. And that's what the O/P and M that are listed up there are. And then we might talk a little bit about some limitations of electrophilic aromatic substitution reactions. So, we can already have a substituent on benzene and have aromatic substitution occur. Okay, the substituents that are on there will either increase or decrease the reaction rate, and they do that by whether or not they donate electrons to the aromatic ring or that they withdraw electrons from the aromatic ring. So think about it for just a second. Imagine we have a benzene ring. If we think about the mechanism, right, of a benzene ring reacting with an electrophile, how do I push the arrows? Where do I start? Yeah, I start with the pi electrons, right? And those electrons, a pair of those electrons are going to go and react with the electrophile, right? So I've got to have electrons moving to the electrophile. So if I have a substituent that actually, by resonance, let's say, puts more electrons in the benzene ring, would that reaction be faster or slower with an electrophile? It would be faster. The more electrons I have in the ring, the more there are to react with the system, right? Now, if I have a substituent that pulls electrons by resonance, let's just say, out of the aromatic ring, is that reaction going to be faster or slower than the reaction with benzene? That one will be slower, right? Electrophiles want to have electrons. So the more electron-rich an aromatic ring is, okay, the faster the reaction. Okay? So electron withdrawing and electron donating groups are going to become very, very important here. So it turns out that if you have an atom that is attached to an aromatic ring, there are a couple of ways in which, and let's just use X, a halogen. Would a halogen add electrons to the benzene ring or remove electrons from the benzene ring? It will remove them by induction because halogens are very electronegative. But what does X have on it on the outside that I've drawn? Lone pairs. And so what can I do by resonance? I can move those into the ring, right? And so we can add electron density to the electron ring by resonance, right? And so we're going to have to figure out what these groups do. Do they add electrons to the ring? Do they remove electrons from the ring? Okay? So we're going to learn what groups do what. Right? So if we look at aniline, for example, aminobenzene, right? The nitrogen, is it electronegative or electropositive? It's electronegative. So it's pulling electrons to itself through the sigma bond. Remember? Electrons are being withdrawn in electronegativity issues through sigma bonds. But the nitrogen also contains what? And a lone pair. And that lone pair on nitrogen, is it going to withdraw electrons from the benzene ring or donate electrons to the benzene ring? It's going to donate them by resonance, right? So even though nitrogen is inductively withdrawing electrons through the sigma bond, the sigma bond's not what makes something aromatic, is it? It's all those pi electrons, right? Now, an alkyl group, okay, does the carbon on that methyl group have a lone pair to donate into the benzene ring? It does not. Is it electronegative? Is it pulling electrons away from the benzene ring? No, carbon and carbon have the same electronegativity, right? Yet this is a electron donating group by induction. Why? A methyl group on an aromatic ring activates the benzene ring. Why? What is there about that methyl group that makes the reaction go faster? Okay. How? It's partially positive.
I guess not partially positive, but the electrons lie with benzene.
What about it, though? Why would it give up electrons inductively to the benzene ring? There is resonance in the benzene ring, but none of the proper resonance structures that I draw account for that. Okay, that's a true statement. Doesn't explain it, though. Okay, it does have 3 hydrogens. Now we're getting somewhere. So it's got 3 hydrogens on it, right? What do those 3 hydrogens do? Is hydrogen electronegative? No. But there are bonds between the carbons and the hydrogens, right? And those bonds are sp3 hybridized. They kind of look more like p orbitals than s orbitals, right? And they've got 2 electrons in them. And those orbitals can actually overlap with the benzene ring. Remember back in 255, we talked briefly about this thing called hyperconjugation, that we can't draw proper resonance structures for it, but it's inductively, through space, putting electrons into the system, right? Same thing's going on here. So alkyl groups are actually activating groups. They make the benzene ring more electron-rich and therefore activate it, okay? So if we look at aniline again, okay, we just determined that the nitrogen is pulling electrons through the sigma bond, but that's not what's important. The lone pair on nitrogen can be donated into the ring, and we can draw all these resonance structures, right? 3 of those resonance structures have what inside the ring? A formal what? A formal negative charge. If you're an electrophile, are you going to want to react with something that is formally negative or something that is formally positive? Formally negative, right? Now, are those negatively charged resonance structures the major contributor? They are not. The major contributors are the ones that you see on the ends, right? But remember what we learned about major and minor contributors. Just because something's a minor contributor doesn't mean it's insignificant, right? And so the fact that we can draw these resonance structures tells us that the aromatic ring of aniline should be more reactive than the aromatic ring of benzene. Right? So if I had aniline and I had benzene, I had a 50-50 mix, and I had an electrophile, which one would it react with? The aniline, not the benzene ring, right? And that's what we're talking about when we're talking about activators and deactivators. How do these reactions occur in terms of rate? Okay? Now, if you take something like benzaldehyde, okay, so a carbonyl-containing group attached to the benzene ring, so here it's just an aldehyde, right? We've got an sp3 hybridized carbon here. We know that this carbon has a partial positive charge on it because of this resonance structure that we can draw, right? Now, this is a minor contributor to the overall resonance hybrid, but it's still a valid resonance structure. That's a positive charge directly attached to the benzene ring. That can pull electrons out of that benzene ring by resonance, right? I can move these electrons here and have a positive charge within the ring. Is this going to activate or deactivate the aromatic ring? It's going to deactivate it. If I'm an electrophile, I'm positively charged. Am I going to react with something that's more positive? No. So actually benzene, unsubstituted benzene, would react a lot faster than benzaldehyde in the electrophilic aromatic substitution reaction. You all are actually going to do this experiment in lab. I forget which substrates you use, but you will use benzaldehyde, I believe, and one other benzene compound, and you will do a competition to see which one gets the electrophile. And it will allow you to see this firsthand through your lab experience that this really does work, that you put a ketone on, or a ketone or an aldehyde on a benzene ring, it's going to react a lot slower. Okay. So, if we look at atoms that are directly attached to the benzene ring, if they have lone pairs of electrons, okay, they are going to activate the ring if it's a nitrogen or an oxygen. If it is a chlorine or a bromine, or just a halogen, yeah, we have the electrons that can be donated into the ring, but it turns out that halogens are so electron withdrawing, they don't like to donate their electrons too well. So they will actually deactivate the ring slightly, okay? So nitrogen and oxygen will activate the ring, whereas chlorine and bromine will slightly deactivate the ring. And it has to do with where these things sit on the periodic table. Okay, so you'll look, chlorine and bromine actually are in different periods, right? Whereas oxygen and nitrogen are in the same period as carbon. Okay? And so it's all about the periodic table why we see this effect, even though there's lone pairs of electrons. Okay? So we just talked about that. We'll skip that. So, let's do a thought experiment. Chase takes benzene, and Nick takes toluene. What is toluene? Methylbenzene. And we take a 50-50 mix of them, mix them together. Okay? And we throw in an electrophile. Which one is going to react the most? Toluene, right? So we have toluene. Just going to draw it up here. And we have benzene. And we take this mixture and react it with the electrophile. Right? Now the electrophile can technically react with either one. And I'm just going to draw a line like this for right now. Okay? Don't really know where it's going to go. But on the benzene, it can go anywhere. It doesn't matter. It's the same product, right? So we could have this, which we are going to say is going to be the minor product because it's deactivated with respect to the toluene. And this is going to be our major product. How many products would you predict that I could get out of that particular reaction with the toluene? I can get 3 different products. What would they be? Well, they are because of resonance structures, but how would we name them? Ortho, meta, and para, right? So that one would be what? And para. Would we get them all in equal amounts? We will not. It depends on what kind of group that is already on benzene. And it turns out that alkyl groups are ortho-para directors. You'll end up with like 95% of the product being a mixture of ortho and para, and very little meta, if any. Okay? So it's this starting group that tells us whether or not it's going to be activated or deactivated. And we've already determined that it's going to be activated because this is a more electron-rich benzene ring. But this group also tells us whether or not it's going to be an ortho-para product, which is what we'll get as our major mixture here, or meta, which is going to be our minor of that one. Okay? So this is where all the confusion comes in. You have to be able to determine what that group is that's already on benzene. Okay? And so if you look at this experiment where they take toluene, they take bromine and iron tribromide, we're going to do an electrophilic aromatic bromination. We do the reaction, and what we find is that about 40%, excuse me, of the reaction product mixture is orthobromotoluene. About 60% of the mixture is parabromotoluene, and we only have a slight trace, just barely detectable amount of the meta. Okay? So what does this tell me? The methyl group is what kind of a director? It's an orthopara director. You need to know that alkyl groups are activators and they are orthopara directors. They direct the new incoming electrophile to the ortho and para position. Yes, ma'am.
If something is an activator, does that mean it always speeds up the rate of the reaction?
Activators, by definition, always speed up the rate of reaction relative to the rate of unsubstituted benzene. Yep.
I have one more question. Can you explain why it's the same, like,
It's the same.
of the orthopara, like, how are those equivalent?
They're not equivalent.
Or not?
They are unique products. They're unique products, but we're going to figure out why it is that we get a mixture of both of them. Okay? We'll get there. So, John runs this reaction. How's he going to figure out whether or not he has ortho, meta, or para? Pardon? NMR would be a great choice. What else might be a good choice? Melting point. If you knew the melting points of the individual substances, how else might we do it? What other techniques do we have that can identify these types of molecules? Could we do it by IR? Technically, yes, but not really easily, right? Why not easily? What information do we easily get from IR? Functional groups. Has the functional groups changed in any of those molecules? No. We would have to be in the fingerprint region, interpreting the fingerprint region to determine whether we had ortho, meta, and para. And what did I tell you all about interpreting the fingerprint region? It's not easy. We don't typically like to do it, right? We typically like to only deal with the functional group region. So IR, although technically you could, probably not a good idea. What other technique do you have that could identify these things? GC. GC would be an excellent choice. These molecules are small, they're volatile. You could shoot them on a GC and we would expect to see what? 2 major peaks and maybe a little tiny blip, right, for that trace, if you're lucky, right? But we'd expect to see one peak that's about 40%, one peak that's about 60% of the overall, right? So alkyl groups are orthopara directors, right? Now, let's say we start off with nitrobenzene. The nitro group, is that going to be an activator or a deactivator? It is a deactivator. And how do I know that? How do you know that, Anna? Okay, that's good. How? Okay, but anilin's nitrogen and it's an activator. So what do I know about the nitro group? What do I need to do? I need to draw the actual Lewis structure, right? And when I do that, what's it look like? Is there? Yeah, but there's actually a formal positive charge on nitrogen. There is a formal positive charge on that nitrogen atom. And so what's that going to do to the ring? Add electrons or take electrons away from the ring? It's going to take electrons away. Okay, both inductively and by resonance. I can draw a resonance structure that pulls the electrons right out of the ring, right? All I've got to do is push the electrons here, like that, and I would have a formal positive charge on that carbon within the ring, right? So nitrobenzene is a deactivator. Anna's right about that. Its reaction will go a heck of a lot slower than the reaction with benzene. But the nitro group is a group that's already there, and any group that comes in, it's going to direct that incoming group, right? And so when we run this reaction, okay, so let's say, I don't know, Kendall's running this reaction. Okay, and so she takes the nitrobenzene, she puts it in with a mixture of nitric acid and sulfuric acid. The electrophile is what? What's the electrophile here? NO2 plus, right? We generate NO2 plus, and we get potentially 3 products, right? And she finds out that this middle one, this meta dinitrobenzene, is 93% of the mix. So this nitro group is what kind of a director? It's a meta director. Now wait a second. We just talked about alkyl groups being activators, and they were ortho-para-directors. This is a deactivator, and it is a meta director. So we're starting to see that activators are typically ortho-para-directors, and that deactivators are going to be meta directors. Okay? So how would we figure this out? How would we figure this one out? The mixture. How would Kendall figure that out? How would she come back and bring us the information? Probably she's going to run a GC, right? She's going to see 3 peaks, maybe. She'll see a little bit of this ortho-substituted product. She'll see a heck of a lot of this meta-substituted product, and if she's lucky, she'll see maybe a trace of the para-substituted product. Okay? And she'll integrate those peaks, and she will get that information to us. Now, I've got some slides that I want to show you, but I wanted us to do a little bit of a thought experiment first. Get a different pen. This one's not working well. Everybody in a purple mood? See what we can do with purple. So explain to me why having a nitro group on the benzene ring puts the electrophile in the meta position. And I'm just going to use a generic electrophile here. I don't care what it is. But this is going to be the major product. How am I going to explain that satisfactorily, other than Dr. Masterson told me this is how it is? I need to draw the mechanism, right? I need to think about the mechanism. But the general electrophilic aromatic substitution reaction mechanism won't explain this by itself. Nowhere in that general EAS mechanism did we ever see a position relationship, right? It just reacts with the aromatic ring, you form a cation that then eliminates a proton and regenerates the aromaticity. It's a simple mechanism. But it doesn't account for whether it's going to be ortho, meta, or para, right? So what do I have to think about here? Pardon? I heard the R word. Resonance. I got to think about resonance structures, right? And when we draw resonance structures, we need to have the complete Lewis diagram, right? Just like I was talking up there for that one, right? So let's draw everything out. There's nitrogen, there's an oxygen, there's an oxygen. Let's put in all the lone pairs, our formal charges, right? How can I draw resonance structures for this? Okay, I can move that there, right? And move what else? Charge is going to stay on nitrogen. Can move that one up, right? Right? That looks like a lot of charges, doesn't it? Can I draw another resonance structure? How do I do that? I can't do that one. But I can move this double bond here, right? So I can move that double bond there. And in so doing, I put the positive charge here. Can I draw another resonance structure? What do you think, Bailey? Actually, I can draw one more. I can move this bond here, right? 50-50. Just had bad luck. Right? Actually, these are the same, really, because the ortho positions are identical. So, in a way, you were almost right. Okay, all right. That's good. That's good. That's good. It's not unique, but it is a different resonance structure because we're not moving the atoms, right? So we really do have to distinguish these. Where does the positive charge always appear? And? And in the ring, but in what locations in the ring? Ortho and para. Where does it never appear? Meta. So if you're an incoming electrophile, where are you going to want to react? Where there's electrons, and where are they? On the meta. There's never a formal positive charge on the meta position when we have an electron withdrawing group on a benzene ring. Never. And electrophiles want to react where there is the most electrons. Now, this reaction is going to be slower than benzene, but nonetheless, there's still going to be more electrons at the meta positions because I never have a formal positive charge there. So that's where it's going to react. Now, if we think about this differently, if we think about aniline, whoops, if I can draw aniline, not pyridine, aniline, how am I going to think about this one? I start with the lone pairs on nitrogen. I can't push any pairs to nitrogen. Why not? What does the nitrogen currently have? Currently has an octet, right? And it has no way for me to push those electrons without breaking the octet rule. But I can push the lone pair, and where am I going to push them? To the ring, right? And so I can push them into the ring. And what do I have to do when I do that? I have to break a pi bond and put those electrons on a carbon. Okay, and so when I do that, notice I have a negative charge on the ortho position. Can I draw another resonance structure? How would I do that? I would move these electrons to the para position. Can I draw another one? Where? The other way around. Just joking, right? All right, good. Where are the electrons always at? Ortho and pair. Where are they never at? Meta, or at least in terms of the negative charge, right? So when I have an electron donating group, something that can donate electrons into the ring, those electrons are going to end up on the ortho and para positions. But they never end up on the meta position by resonance. And electrophiles want electrons. They're going to react where the electrons are. If I have an electron withdrawing group, the electrons are on the meta position. If I have an electron donating group, those electrons are on the ortho and para positions. Now wait a second. I have twice the number of resonance structures that put electrons on the ortho position, and I only have one resonance structure that puts electrons on the para position, right? But which one's going to be the major product? Para. Why? Exactly. You got it. The para position is unhindered. For it to react here, it's got to get close to that other group. Okay? So the para product is typically the major product in an ortho-para product that you might predict from this type of a reaction. Okay? Because of steric crowding. Okay? You all need to commit to memory these substituents and what they are. You will not have a note card for next exam. You need to have these committed to memory. You need to know what are ortho-para-directors, meta-directors, activators, and deactivators. And I'm going to hold you responsible for these, okay? If you have an atom that is bound to the benzene ring, like a nitrogen in an amino group, whether it's primary, secondary, or tertiary, those are going to be activators. Alcohols, phenols, for example, the oxygen is an activator. Ethers, activators, okay? The nitrogen that's directly attached to the aromatic ring here, okay, even though this is an amide, okay, it's an activator. And then, of course, alkyl groups, all alkyl groups, okay? Notice the relative amount of activating they are. What can you say from that? Amino groups are the best, followed by hydroxy groups, followed by ethers, followed by amides, followed by alkyl groups. These are all ortho-para-directors, and they are activators. So if we started off with toluene and we brominated it, we would expect to get a mixture of ortho and para-bromo-toluene. And we would expect that the para substituent would be the majority of it. If we had phenol, hydroxybenzene, and we brominated it, we would expect it to give us ortho and para halogenated product, right? Ortho, para, activator. Okay? Now, I'm going to come back to 2. So let's just focus on 3 for right now. Meta-directors. All meta-directors deactivate the ring. By definition, if it's a meta-director, it has to be a deactivator. Okay? These are things where the carbon atom directly attached to the benzene ring is a part of a carbonyl. So aldehydes, ketones, esters, carboxylic acids, nitriles, sulfonic acids, nitro groups, and positively charged tetraalkyl ammonium salts. Okay? These are deactivators. Notice these are really strong deactivators, the nitro group and the tetraalkyl ammonium salt. So if we think about making, let's take ourselves back a long time ago when we actually used to make this little molecule in the United States. It was very useful. What is that? Pardon? TNT. Is that what you said? Okay, good. TNT, trinitro-toluene. What is it? It's an explosive, right? How are the nitro groups with respect to the methyl group? They're ortho and para, right? So what do you think they start with? They start with toluene. They take toluene, they put it in a mixture of nitric and sulfuric acids. The first nitro group goes on pretty easily. Where does it go? Goes to the para position. Okay? The second nitro group goes on a little more difficult. Why? It's disubstitute, but we have an alkyl group, which is an activator, and we have a nitro group, which is a... What's the nitro group? It's a deactivator. Is it a weak deactivator or a strong deactivator? Is the alkyl group a strong activator or a weak activator? Ah. So the nitro group's going to take, it's going to be the prominent thing here, right? So that second nitro group goes on, but it goes on kind of hard. It's hard to do. How about that third nitro group? Super hard. And that's where you start to run into kabooms. All right? So making nitrotoluene, no problem. Dinitrotoluene, be careful. Trinitrotoluene, you got to heat it up, you got to do stuff. Usually not a good idea with explosives, right? A lot of people lost their lives just making the stuff, okay? Because as we put more nitro groups on, we had more and more deactivation of the ring, and it made the next one harder and harder to go on, okay? So everything in this category is going to be a meta-director, and it's going to deactivate the ring. So that's pretty easy. Activators are orthopara. Deactivators are meta, but there's a special class for the halogens in the middle. They are orthopara directors, but they are deactivators. Why? They really don't want to give up their electrons too well. They don't want to donate them to the ring, right? So inductively, they're pulling electrons to themselves, right? And that deactivates the ring. But why are they orthopara directors? They do a little bit, right? And so when we draw resonance structures, you will still see that those electrons from the halogen will end up by resonance at the ortho and para positions. But they don't donate a whole lot of electron density to the ring because they are so electron withdrawing, okay? So you need to have those three categories of things committed to memory. Activators are what? Orthopara directors. Those the meta directors are all deactivating, and the halogens are a special case. They are deactivating orthopara. Okay? Meaning that if we started off with, let's say, fluorobenzene and a mixture of benzene, 1-to-1, and we threw in some bromine and some iron tribromide, what would happen? Of the fluorobenzene, right? You'd end up with the para position. But would you end up with more of that product or just more bromobenzene? Yeah, because benzene is more reactive than fluorobenzene, right? Because fluorobenzene would be deactivated. Okay? So here's a way that some people remember it. If your group here has a lone pair and it's nitrogen or oxygen, it's going to be an activated ring. If Z happens to be a halogen, it's going to be a deactivated ring, right? And of course, alkyl groups are always they're always activators and orthopara directors, right? That's kind of important. Okay? So now in your own words, I want you to take just a couple of minutes and I want you to write for me a few sentences. Why do certain groups activate or deactivate a ring? And I want you to turn this in to me at the end. So write it on a clean piece of paper. I want in your words why certain groups activate and deactivate the ring. You need to be able to understand this at the I can say it in English understanding level. You need to explain it in your own words, not my words.
Oh, yeah. Like bullet points or
I don't care how you explain it. Just in English.
super detail?
Stupid detail?
Super, but I meant to say super.
Ah. I'm not interested in where they go, which would be a steric hindrance argument. just activation and deactivation. Another 2 minutes. All right. So why does an activator activate a ring?
Because they can donate electrons to the ring.
That's right. They make the ring more electron rich. Why does a deactivator deactivate the ring? Pulls electrons out of the ring, right? It makes it electron deficient. That's the concept, right? That's the concept. Activators activate the ring by adding electrons to it through resonance or hyperconjugation, but somehow, right? And so that's the easy way to understand it. That's how I actually understand activators and deactivators, okay? But you can also look at it in terms of energy diagrams, right? And so here's benzene that's unsubstituted, right? The electrophilic aromatic substitution reaction occurs by the lone pair reacting with the electrophile. That goes through a transition state, and we have this resonance stabilized carbocation as an intermediate, right? And it has a certain energy of activation. Now, if I add an electron donating group, which is what D is, what does that do to the energy of the transition state? It lowers it, right? And it lowers it, why? Whose postulate? Yeah. Good. Right? The transition state is closest in energy to the carbocation. Anything that can stabilize that carbocation, by definition, also has to stabilize the transition state, right? And so the transition state for the reaction is lower. If the transition state is lower, the reaction goes faster. Smaller hill decline. However, if we have an electron withdrawing group, right? If I take electrons away from a carbocation, does that stabilize it or destabilize it? It destabilizes it. It raises the energy, and so therefore the energy of the transition state also must go up, right? So this reaction is going to be slower than benzene. This reaction is going to be faster than benzene. Activators and deactivators. That's the real reason. But I simply think of it as donating electrons, removing electrons, okay? Both of those are equally good explanations, okay? So, when you need to evaluate whether or not a particular substituent is going to give you orthopara or meta, you need to look at the original substituent. In our case, when we looked at toluene, the substituent that's on there is the methyl group, and it is a orthopara director and an activator, right? So we're going to end up with products at both the ortho and para sites, right? So if you look at the example here, you can actually draw out all the resonance structures. I will not ask you to do this on an exam. It just takes too much time. But you need to understand it here, right? So if we have an electrophile reacting with toluene, right, and we put it on the ortho position, what you'll find is that you can actually draw one of the carbocations that's going to be highly stabilized, because this is tertiary, right? It's resonance and tertiary. So does that favor ortho substitution or disfavor it? Favors it. If we look at meta, if I put the electrophile in the meta position, notice I can never put that carbocation and make it tertiary. So is that going to stabilize or destabilize it? Destabilize it, right? Likewise, if I do the para attack, I can get to that same stabilized carbocation intermediate, okay? And so, Anna, why is it that the para is going to be greater than the ortho? Steric hindrance. The electrophile comes in at the ortho position, it's going to run into those hydrogens on the methyl group. It's crowded. The para position, it doesn't have any of those interactions. And so you're going to almost always find that the para substitution is the major product in an ortho-para. Now, sometimes it can be really close, depending on the size of the substituent, but almost always, if you're betting, bet that the para substituted product is going to be the greatest amount. All right, so we're going to skip that one because you all can go through that on your own. Okay? Skip that one as well. Now, there are some activating groups that are extremely strong. The amino group is a very strong electron donating group. Okay? So if we start off with aniline and we try to brominate it using bromine and iron tribromide, we actually get tribromoaniline as the product. Very hard to just put on one bromo group because the aniline is such an activated ring, it overreacts. So if you want to make, it overreacts. So if you want to make a tribrominated aniline, this is a great way to do it. If you want to make monosubstituted aniline, a little more difficult. Okay? Phenol is the same way. Again, the OH group's a very strong activating group. If we look at our list, right? If we do this reaction with bromine in the presence of iron tribromide, we're going to get tribromophenol. Okay? As the major product. However, it turns out that you can take phenol and just react it with bromine, no iron. This reaction will go, but it stops at the monosubstitution. It's such a strong activating group, the hydroxy, that it will react just with molecular bromine. Okay? And you would end up with ortho bromophenol and para bromophenol. And which one would be the major product? Para. And how would we determine that? You could do it by GC. Well, it is that's the explanation. But to determine it, we would determine it by GC, maybe TLC or something along those lines. Okay? All right. We didn't get as far as I wanted to get today, but that's all right. We've only got about a minute left. On your way out, put your written explanation up front. Now, I'm going to try to post something to YouTube later this evening to finish the slides that we need to finish. You all have to watch that before class on Friday. We're going to do our inverted lecture, which was originally scheduled for today. We'll do that Friday. That'll give you the weekend to work on it and get it back on Monday. Have a good one.